So it's our great pleasure to invite Professor Maxim Pospelov from Minnesota University and William B. Fine Institute for Theoretical Physics to give a lecture for us. And he received his PhD degree in physics from the Novosibirsk University in Russia in 1995. He has been on postdoc position in the US, Canada, and the UK. And from 2002 to 2019, he worked as a faculty at University of Victoria in Canada and Perimeter Institute. His interests include particle physics and cosmology, and the talk title today is Accelerated Light Dark Matter. So let's welcome our speaker. So please start.
All right, thank you so much. Let me share my screen, if that worked. I'll move this thing. I'll move this down, and I go to the full screen. All right. Did it work?
Yes.
Very nice.
It works.
Okay. So maybe I can move that one away. Thank you very much for assembling to listen to me, and I'm going to give you an overview of the works I've been doing in light dark matter mostly, but not necessarily all papers here on light dark matter. But the idea, the overriding motivation is to get the most out of the existing dark matter experiments. And I'm happily acknowledge here the collaboration with various people, including a group at Triumph, now a new graduate student at Harvard, Brinkman is in Oslo, Pradler in Vienna, Ritz in Victoria, and of course, a very important component to our collaboration here is the group led by Hapong An at Tsinghua University in Haomingna as well. Very good. Let's see. Why identifying dark matter is difficult? We know, of course, from the cosmology rather well that the dark matter was in place since at least the matter radiation equality, and it constitutes roughly almost a quarter of the observable balance of energy density, and it distinguishes itself from dark energy by its ability to cluster and form structures. And of course, baryons are vastly insufficient to do that. So in our galaxy, we believe, we know, at least in the solar neighborhood, quite a bit, there is quite a bit of dark matter on the order of maybe 1 GeV per cubic centimeter, slightly less. But these are deceiving units because they kind of presume that we know that there is dark matter could be as small as cubic centimeter. In fact, we don't, right? So the smallest distance scales on which we see dark matter is 10 to the 21 centimeters, and the experiments are performed, and a lot of investment went there in the labs at a small kind of distance. Compared to that, we need to extrapolate 19 orders of magnitude, and this can only be done with the help of theory. So one has to have a theory behind the whole business. Very well. So we kind of think that dark matter could be a new type of particles. This is not set in stone, but the simplicity of the early universe makes many of us suspect that this is so. After all, the whole cosmology is described by a 6-parameter model called lambda CDM, and it works really well, especially on large scales. Now, search for dark matter is done at colliders, recently at beam dump experiments, and most importantly, in low radiation environments such as underground laboratories. So the goal for this talk is to explore multiple collisions of dark matter to fill in blind spots to certain type of dark matter that otherwise cannot be seen by traditional experiments. So let's just flash briefly the examples of the standard model dark matter interactions. If the interactions are sizable, the dark matter is populated in the early universe, and then it's self-depopulates itself into the right level by annihilating via perhaps some unknown particles, or maybe through the standard model force carriers, such as Z boson or Higgs boson, into the standard model states, and then this process freezes at a right moment, giving the observable amount of dark matter if the annihilation process is at the level of so sigma dot v relative velocity is at the level of 10 minus 36 centimeters squared times the speed of light. Historically, of course, very importantly, the super partners models with supersymmetry were a driving force behind many of these developments. In recent years, there are a lot of interest being towards models where lighter particles participate in the mediation. So here is the model where a photon mixes with a dark photon, talks to the dark matter, and that connects the standard model states to this chi particle. So the theoretical framework for where I'm going to be working with is kind of a standard model plus effective theory as an effective theory, where you encode high dimensional operators in terms of dimension 5 and 6 and so on. But if there are actual lightish degrees of freedom, such as light dark matter or mediators, we also include it as explicitly as dark states, and the interactions between the standard model and the dark states at lowest dimensions they're well known, and they're being extensively classified and studied. For example, right, if we stick to the models where the force is mediated, say, by the weak bosons of the standard model, it's very hard to build a reliable and not excluded model of the light dark matter. But if there is an additional extra force here mediated by the dark photon, the models can accommodate very light dark matter. And then similarly, if there is a new force that through the boson that mixes with the Higgs due to the trilinear term, you can also build these models. I and my late colleague Mikhail Voloshin have written a bunch of well, a couple of papers on along these lines long time ago, and since then this topic gained in popularity. All right, so let's look at the dark matter detection. This field, I wouldn't be exaggeration to say that this field is dominated by the largest and cleanest experiments, such as experiments based on the dual phase xenon TPCs that have exquisite information about the events that if the dark matter scatters, so basically if we kind of put this diagram from S channel to the T channel, we can get a scattering. And if dark matter scatters on the nucleus or an electron, you typically get the initial scintillation and then the drift of ionization followed by another burst of scintillation. So using this method, the three collaborations here have advanced the sensitivity to dark matter nuclear scattering very well. And this is the result of the sort of xenon one-ton initial search for the nuclear stellar model dark matter nuclear interaction. They were not finding it with a high fidelity, excluding a lot of parameter space. However, the sensitivity sort of disappears as we go towards lower and lower masses, which, as I argued, are not excluded. And that is, of course, related to the fact that the recoil falls below the experimental threshold. So kind of looking at this picture, it's kind of clear that we're moving this main part of the curve down. It's an enormous investment, and it's mostly an experimental business. But sort of gaining sensitivity to the left of that curve is, in some sense, also open field for theorists, because you can also be clever and somehow use some tricks to fill it in. It also was interesting that in 2020 there was some hint on excess in electron recoil, although it doesn't look particularly convincing, this excess, and now we know that it is gone. Most importantly, however, that the event rates that xenon one-ton collaboration could probe are going down to 60 events per ton per year per keV in a very small energy release range. And this year there was important announcements by LZ collaboration that improved on the xenon one-ton results in the nucleon WIMP scattering. And they also released their electron recoil data, where you see the peak, which they have identified with argon-37 peak, and there is nothing funny or secret about it. And they argue that this might have been the remnant of that peak might have been behind the xenon one-ton excess. Now, the xenon n-ton, the successor of one-ton, has also released their spectrum. And this is electron recoil spectrum. So the scale here, look, used to be like 60 events per ton per year per keV. Now we're going down to tens of events per, and so this is exquisitely improving the sensitivity. There is no sign of the peak, but look at this. This is like slightly off topic, but this is a very, very significant development. This is the discovery of double electron capture on xenon 124. This is the process that exists in roughly maybe 3 or 4 nuclei in nature, never being seen directly before. And now for xenon n-ton, this becomes a calibration line. What you see is the electrons disappear from 2 subshells, and the energy release is the filling of the shells. And this becomes you can even see the structure due to the subshells. This is a really impressive developments. Okay, so now I'd like to use this very, very sensitive data to gain information about light dark matter. So we come to the point of formulating the blind spots for direct detection. One blind spot is obviously here, when the particle's kinetic energy is insufficient to ionize atoms. or move the nucleus. For example, if I take an MeV scale dark matter and multiply it by its typical velocity, I get to the kinetic energies of 1 electron volts. And to ionize xenon, you need at least 13. So this is not going to work, obviously, for MeV scale dark matter. And another blind spot is actually usually overlooked by people. If you have a strongly interacting but subdominant component of dark matter, then particles quickly thermalize. They reach the typical kinetic energies of 0.03 electron volts, which is 300 kelvins, and this is also much below the thresholds. So these are the two blind spots in direct detection that one can very readily identify, and therefore we are going to try to cover them. So going back to the 2017, that this is the representative slide where there are electron recoil data, constraints from xenon 10, xenon 100 experiments, and there are no limits here below 10 MeV, which we were finding as slightly upsetting. And then people were suggesting that the researchers, this is still a very active field of research, suggesting trying to experimentally lower the thresholds by using various advanced techniques. So one can have semiconductors with very small gap, and this way gain information about this area over here, and the amount of papers written on it is quite significant, with many advanced condensed matter techniques being suggested. The problem with that is that nobody has any slightest idea what the backgrounds for this business is going to be. So just to summarize the experimental picture, we saw from the LZ and xenon Anton experiments that the event rate as low as 10 events per ton per year per keV is possible for recoils at the keV scale and larger for electron recoils. Now, if you look at the slides from this year, identification of dark matter conference, they had a lot of work reported on this novel devices with the small thresholds, and the counting rates here are not per ton per year, but per kilogram per day, and they're not 10, but 10 to the 7. So so there are some instrumental excess that they cannot identify thus far. So this is just on the surface of it. The counting rates here are like 10 or 12 orders of magnitude larger than in the xenon type of experiments. And so I like to use these small rates. So what we're going to do is the following. Here is the cartoon of the distribution of the dark matter particles over the velocity. So it's supposed to be some type of Maxwellian distribution, but Maxwellian distribution has an exponential tail extending to very far. Here, however, we know that the galaxy can retain only particles that are bound to it, right? So therefore, there is a kind of around us a separation velocity that particles would have to have an endpoint to the spectrum. Okay, so this picture is a little bit naive. So what we're going to say is that there is a small but a finite kind of tail sticking out in that direction and extending to much higher energies. And that is true for dark matter scattering on electrons and dark matter scattering on nucleons. Here comes the main idea in our paper with Haipeng and Haoming and others. So basically, let's consider a dark matter traversing the sun. Let's say it traverses the core region of the sun, okay? The size of the core is 10 to the 10 centimeters. The average density there is 10 to the 26 per cubic centimeter. So I will multiply this number, and I will get 10 to the 36 inverse centimeters squared. Now, to calculate the probability of the scattering, I will multiply it by a typical scattering cross-section. Let me take as 10 to the minus 36 as the scattering cross-section. Therefore, I will get a probability on the order 1 for the dark matter to experience a kick by an electron. Now, what we need to know about these electrons inside the sun, that they're very, very fast. Indeed, their velocity is the square root from the ratio of the core temperature to the mass of the electron, and it has a very fast fraction because it's Maxwell-Boltzmann distribution there, right? So the electrons inside the sun can move as fast as 10% from the speed of light very easily. And so if I have a dark matter matching in mass to the electron mass, for example, then any collision that I just argued that can occur sometimes with the probability order 1 will impart some of that velocity to the dark matter, and we will have a very energetic fraction of dark matter coming out of the sun. So dark matter, therefore, imports some kinetic energy, right, by going through the sun. This is very similar to, I don't know, Sunyaev-Zeldovich effect, where the CMB photons going through a very hot plasma and being, through scattering being made much harder than they are, well, a little bit harder than they are. And so here is the simulated distribution for different cross sections from our first paper. That this is the work by Haipeng. He has written the code for simulation, and this is the sort of that part of the curve is the endpoint here for the galactic velocity distribution, and this is a large distribution, and then we have a small component sticking out. So if we estimate the probability of this component of the flux, assuming that there is a order 1 event here, then it's clear that we are going to have a penalty of 10 to the minus 6. And that is because clearly the main penalty would be that the sun looks small on the sky. It subtends at the core of the sun only about 10 to the minus 6 of the solar solid angle, and that is where the main suppression comes from. So, but the overall numerical simulations, they confirm the naive kind of estimate of what the size of the reflected spectrum component can be. So using this simulated spectrum that was improved for the 2021 paper, we get a flux of fast particles, of fast dark matter particles accelerated by solar electrons. And using that, one can see how we can calculate how efficiently they're going to induce ionization in xenon type of experiments. And therefore, we can set the bounds if the number of events is above what the collaboration observes. So these are the limits we derived through using xenon one-ton experiment. Here on the right, this is the interaction via dark photon, and here on the left is the interaction on electrons only. So there was a similar papers written by Emken. So you can see that the sensitivity here, roughly from 5 MeV to 0.1 MeV, is really a world-leading sensitivity, and we have covered this parameter space very nicely, which is a big advance here. Also, I should say that, say at the nominal energy of a mass of 1 MeV, the results from the experiments that look to lower the threshold are very, very far away by many orders of magnitude. We have also performed similar calculations for so the previous case was for the sort of heavier compared to the momentum transfer mediators, so it's a contact limit for the cross section. And the second example here is the exchange of nearly massless dark photon, which corresponds to roughly what one would call a millicharge particles. And there, the sensitivity as well, we can put a strong limit, but the competition from these new experiments is much stronger because they can rely on much softer collisions, thereby benefiting from enhanced cross-section. Now, this is, if we translate this into an effective charge in units of electron charge, we are sensitive to, through this method, to the dark matter on the order of charged on the order of 10⁻⁹, which is very, very, very nice result. Here I was trying to add, it didn't come up very nicely, trying to add with the help of Josef Pradler, the rescaled results from xenon Anton experiment. If we add that, there is basically you remember where the counting rates are below the xenon 1-ton counting rates by a factor of 6. So the results are going to be rescaled roughly by the square root of 6 because we use 2 collisions. So we are not linearly sensitive, but quadratically sensitive to the cross sections on electrons. Very well. So I'm done with that part of the talk, and I want to cover some other topics now. So let's try to play this game with other type of scattering. So suppose I have scattering of light dark matter on protons or nucleons in general, right? So one way would be to maybe pair produce the dark matter and try to see that in the beam dump style experiments. I've worked extensively on that, but also there is sort of a benefit from exploring this picture of elastic cross-section of dark matter on nucleons in general, right? So here, I'd like to use the fact that the galaxy has a non-vanishing component of cosmic rays. We know a lot about them, cosmic rays. They around us, they peak at roughly GeV kinetic energy. Their density is 1 per centimeter squared per second. And the flux, and we can play the same game. So if the cosmic ray protons scatter on dark matter, they can upscatter it to almost arbitrary velocity. And what's pictured here from our paper with Torsten Brinkmann is the main flux of dark matter. SHM here stands for standard halo model, and there are some for various sizes of the cross sections, some or masses. There are some sort of higher energy components superimposed on it, so they're much smaller by 10 orders of magnitude, but still they're non-vanishing. vanishing. Now, once you go to the really much larger energies than the keV, then it's a question what's better to use in that situation. Is it the dark matter detectors, or it may be the neutrino detectors that have, you know, the best counting rates there. If you take the Super Kamiokande detector, it has sensitivity to a handful of events in the interval of say 10 to 20 MeV, around 20 MeV recoil for 20 kiloton fiducial mass per year, per several years. So this is even smaller than the xenon and ton experiment counting rates. So very impressive. So one could use also the neutrino experiments to set bounds. Here the bounds from our paper that where we have derived, and the bounds are like have two sides to it. So if you take xenon 1 ton, you can see that if you move below that line, you don't have much sensitivity because the reflected from cosmic ray flux is very small. But if you go above that line, the particles actually don't have enough. The xenon is very deep, so you don't get these particles at these energies down below the grand Sasso line. So, but in the middle here, you say if the cross section is something like 10 minus 29 or 10 minus 30 centimeters, you have you know, the detector would have been lit by these particles. So this in the middle here is absolutely firmly excluded. And you can play the same games with the spin-dependent cross-section, because the main component of the cosmic ray flux is, for example, protons, right? So it's guaranteed that you would have the spin-dependent scattering and so on. And there we were using Borexino, but there were also some blind spots left, which were covered by other groups, for example, by Beacom and Capiella, who pointed out that diabase is right at the right depth that you can cover that blind spot as well. And you can see the projection from Juno experiment in their paper. And this topic has gained some popularity, I should say, and I even noticed that the group in Nanjing also have worked on this. Very well. Now I'm moving on to yet another topic, and I want to see if I can cover something also quite perhaps quite exotic, but it is a blind spot, all right. So the blind spot is for strongly interacting dark matter particles, not necessarily through the QCD force, but with the sizable cross sections that, you know, like if the cross sections are 10 minus 28, that's not particularly large cross sections, but these particles never have, they thermalize before they reach xenon type experiments. And so I'm going to be using that situation. And so if these particles constitute a large fraction of dark matter, say F, on the F stands for the fraction. If it's order 1, then the experiments that are being put on the balloons, they exclude that possibility actually. But if for subdominant F, you don't exclude this possibility at all. And so it's interesting how one can you know, access that. So first, I'd like to introduce a concept of traffic jam that we have called it. So basically, if a particle with a sizable cross section enters the the material, it undergoes rapid thermalization, let's say, with a subsequent Brownian motion. And if the mass is significant, then there is also basically a biased Brownian motion down towards the center of the Earth. If the mass is in a few GeV range, then sooner or later, if the particles don't annihilate, there is an upward coming flux. So because of the conservation of the flux, it's very easy to understand that the sinking velocity that we called here terminal velocity would determine how many particles there are there. And if the sinking velocity is 1 per centimeter per second, which is kind of typical for many cross sections we consider, you get 6-7 orders of magnitude enhancement in the density here. Very well. So here is the contour plot. The dark matter traffic jam is it's here, sort of 6 orders of magnitude kind of enhancement. But for a few GeV mass, these particles distribute themselves almost uniformly throughout the volume of the Earth, and you can have 14 orders of magnitude enhancement in their densities. So you may actually start with a very small abundances, but over time you build them up. Okay, so we kind of speculate that this can be used as a certain sort of again dual detection scheme that would also use multiple collisions of dark matter. So it turns out that a number of underground laboratories have, a small number of underground laboratories have underground nuclear accelerators. They're built not for the dark matter purposes, but for studying the nuclear reactions at very in the very clean environments. One such experiment is called Luna, and it's in the Grand Sasso laboratory. So you have an accelerator for 400 keV, and now they're bringing down an accelerator of 3 MeV with a significant current, I should say. And another experiment, although I know very little of it, is JUNA. And it's not Juno, which is a neutrino experiment, but JUNA experiment. And I believe it's in China, okay? Perhaps in Jinping lab. And so the idea is that to run this to run the beam, and this enhanced density of dark matter would sometimes make collisions with the beam, and you would sometimes lose particles from the beam, but that's not going to be observable because there is a lot of residual gas in the tube and so on, and perhaps more than dark matter, you would not be able to have a very precise measurement due to the depletion of, say, protons in that beam. But you will accelerate some of the dark matter particles, and you can have here's a concept of some dark matter detectors shielded nearby. The shielding will easily stop an MeV proton beam, or you can divert it using the magnetic field. But the dark matter goes straight and causes a recoil proportional to the sort of time traveled through this. If the absorption length is not that small. So this is a good possibility. So we have investigated what one can achieve for different masses of dark matter for initial beam energies of a keV or an MeV, and you can see that, say, if the dark matter has say 2 GeV in mass, for example, you can have subsequent kinetic energy of it very easily reaching almost an MeV, and that's very promising, because that's enough energy to make a very noticeable signal in the dark matter detectors. So we have analyzed the sensitivity to the nucleon dark matter cross sections as a function of the dark matter mass and as a function of the fraction. So if the dark matter is having order 1 fraction, we have the best sensitivity, but guess what? This situation is already pretty much ruled out by the combination of various on the surface dark matter experiments or in the balloon experiments. But once you start moving to abundances of 10⁻³ you start having blind spots that I was talking about. 10⁻⁶, almost everything is open here, and these are the tentative sort of sensitivity curves that one can achieve with various types of beams, proton beam, and these are nuclear accelerators. So it could be a carbon beam, or we have also considered some other exotic possibilities. So that is the experiment in China, I believe, that I was talking about, that I noticed that started producing science results recently. Very well. So moving on. So this is an so we are looking for customers. So this is an idea that I believe is possible to implement experimentally. This can be run as I believe can be run as a parasitic scheme. So if you place a well-shielded detector in the line of sight of this accelerators, you can have it operational with, hopefully without interfering with the main nuclear astrophysics program that you can pursue still. With one exception, some of these reactions also produce neutrons. You don't want that. You want the reactions that don't produce neutrons, because neutrons will create the backgrounds for the dark matter experiments. All right. So I also noticed that your group studies various exotic resonances and so on, and I wanted to cover, perhaps in the remaining 10 minutes or so, some funny idea that we had with this group, Berlin, Liu, and Ramani, on making bound states of dark matter and the nucleus. Well, I should say, again, with Pradler and Haipeng, we have studied sort of a possibility of bound state between exotic charged particles and the nuclei a long time ago. But recently we revisited this question with Berlin, Liu, and Ramani. Let's consider that my favorite model that is very simple, heavy dark matter here, and then a mediator that is perhaps a few MeV in mass, 10 MeV, 20 MeV, and there is a mixing parameter here. So let's make let's make this parameter maximal, 10⁻³ or something like that. 10⁻² will be excluded already. The mass in that range, and notice that the 10 MeV mass would create a range for the force much longer, a little bit longer than this size of the nucleus itself. And let's have a heavy particle. So, and then it can be positive or negative. And the negative one will have an attractive force. So all what I was saying so far here was not really sensitive to the sign of the force. But now, if the sign of the force is attractive and the interaction is strong enough, it turns out that heavy nuclei, and it's important, heavy nuclei can form bound states with dark matter. So it's very easy to consider the kind of Yukawa potential modified for the charge distribution inside the nucleus and investigate this question in detail, which we've done. And it turns out that if we go to the sort of dark photon exclusion plot here in this region, I will be covered in some future experiments, hopefully. You can have efficient formation of dark matter nucleus bound states. So interestingly, with xenon, if you have, you can have a bound state of the following form. So if my epsilon parameter is at the level of 10⁻³ and I tune the bound state energy to 2 keV and the mass of the mediator is 15 MeV, I have like a 30 Fermi kind of a bound state size, and that's quite interesting. This again, notice that these are the energy releases right in the kind of range where xenon is sensitive. So then what can happen is that these particles, first of all, they will thermalize. They will be very slow. They will have large cross sections, but you will not notice them. But from time to time, they will form a bound state with a nucleus, ejecting energy. It turns out that the main process by which it does so, the external slow particle comes in, it forms a bound state with the nucleus, and now the nucleus is spread over the 30 Fermi kind of a radius, roughly speaking, in the example I showed you before. So the charge distribution suddenly changes for a nucleus, and that in itself creates a perturbation for the electron orbits and can eject the electron out. So this is a more efficient process than emission of a photon. So we have gone through this calculation. I won't bother you with that. The cross section is actually quite large. It's the cross sections, typical cross sections, you get 10 to minus 33 centimeters squared, but that's sigma v. So, and the velocities are very, very small. So you get 10 to minus 27 centimeters squared, large cross sections. So here's the plot that now the cross section is no longer kind of a variable here, but what's we leave varying, this is the fraction of these particles that can form the bound state with dark matter. And so if you have a xenon type experiment with the counting rates as we have at 2.5 keV, for example, this was the times of still xenon 1 ton excess. So we were kind of aiming for that bound state energy. So you have the release of kinetic energy in form of this electron being ejected, and you have an incredible sensitivity to the abundance of such particles, as low as 10 to minus 16. And the uncertainty here is actually large, and it's completely environmental. It depends on how much of the barium atoms there are above the Grand Sasso laboratory, and there is a significant uncertainty there. And if there is lots and lots, they can actually intercept these dark matter particles on the way. So the point I'd like to stress here, that the dark matter experiments also is some sort of a rarity frontier, right? It can detect the presence of strongly interacting particles that have abundances as little as 10 to minus 16 from the abundances of the dark matter. So, and the kind of where this process occurs is this is again dark matter kinetic mixing versus the mass parameter space, and that's in this corner. Roughly this whole thing occurs. And that will be explored in some future experiments. So, all right, I've been talking to you 50 minutes non-stop. I think it's time for me to stop my talk and answer questions. Let me conclude. Now it's the right time to do the dark matter research. There is so much investment into the dark matter search program all over the world. And we have to, as theorists, use and experimentalists use maximize the use of the funds invested into this. So all my attempts here today were to create some additional sort of creative schemes where you can cover some corners of parameter space that are not captured by the main searches. And I have argued that together with Haipeng, Pradler, and Ritz, and Nai, we have set the best world leading limits in this mass range for the scattering on of dark matter on electrons. And we can also limit the dark matter scattering with protons using the reflection on cosmic rays. One can have new sort of schemes for detecting dark matter using underground accelerators. This is I wouldn't be telling you a lie that I always wanted to use this dark matter, the nuclear accelerators underground for some sort of dark matter, dark sector research. And I think there is a lot of potential there, underexplored potential, or not at all explored. So that's a promising idea. And yet another use of the dark matter experiments is to look for the formation of the bound states between the dark matter and the normal nuclei, and that can occur if the force is indeed mediated by a dark photon, and that parameter space is far from being excluded yet. Okay, I'll stop here. Thank you.
Okay, thank you for a very nice talk. And is there any question or comment?
Hi, Maxim. May I ask a question? Very good talk.
Thank you.
Yeah, so you mentioned use the underground accelerators plus the dark matter detectors. Are there any requirements between the distance between the accelerator and the dark matter detectors?
Could you repeat the question? Is there any distance?
Yeah, no, the requirements on the distance. Between the accelerator and the detectors.
Right.
So are there any, should we put them separately?
Good. So the dark matter, let's say beam, the secondary beam that we get, it's not very focused if the cross sections are kind of uniform. So basically what happens is that the proton beam goes through, and usually this for Luna, this is typically a couple of meters of the beam pipe where it goes before it kind of splits into the say two beams, and they use two stations typically to study nuclear astrophysics, right? So this 2 meters that this beam goes is roughly a diffuse target with dark matter, because it's the idea it's everywhere, right? And then these dark matter particles that emerge, they're not very focused, right? They're kind of spraying around, but they're somewhat forward, but they're more like spraying around. And then therefore it's clear that it wouldn't be advantageous to go tens of meters away, because your flux will go down. But if you are And that will depend on the size of the cover, right? So if you are maybe 4 or 5 meters away, then it's still okay. And usually people also worry that, you know, those of us who come from high energy physics backgrounds, right? You worry immediately. Oh wow, these are beams and so on. What happens? But we are used to, you know, the high energy beams that have the hadronic interaction length of 10 centimeter and so on, and you need a lot of shielding. These things, they don't go far, right? It's a few millimeters of shielding stops the one MeV proton beam for sure, right? So it's more of a study of intrinsic backgrounds in the cavern and making sure, you know, like also you have to have a shielding for the dark matter detector, and it becomes an experimental question of, let's say you assume a certain cross section for the dark matter, right? If you put way too much shielding, it will be stuck in the shielding, right? So if you put way too little, you get too much of a background. So if there is interest in that direction, we would, of course, happily investigate more specific experimental arrangements. We haven't done so because this is like a concept we suggest.
Yeah, because I'm asking because you mentioned Juna. Juna is in China, and so there we already have the CDEX and the PandaX experiments. And
that's precisely the point, right? Could there be some say you cannot move Panda X to the next to Juna. I fully understand that, right? But if you can take some sort of maybe a smaller version of CDEX and place it not too far away, right? Well, first of all, yeah, I think I don't think that CDEX and Juna are in the same hole, right? They're probably in the somewhat spatially separated, but yeah. So that's but one could have a dedicated, maybe not as perfect a detector as CDEX, but nearby, right? That's the idea.
Yeah, that's true. Okay, thank you.
Hi, Maxim. I have a comment about your last topic, the bound state one. So
right.
So remember we had a paper with Bertrand and Yue Zhang about this production of dark bound state directly from the inside colliders.
Right. Yes, I remember.
I think that could cover some parameter space in your plot.
Right, but perhaps, but what we are looking here is the you know, the sensitivity for us goes all the way to 10 to the 4 GeV. So this is a place where we don't stay with the light particles, right?
Yes. In that case,
so the LHC stops here, right?
Yeah. But here so here you have to assume that it is an asymmetric dark matter, right? So a small component of.
Well, we assume that it is a very tiny component. We don't have a very
yes.
We don't have a very coherent story of why there are so few of these particles, right? We wanted to show that these detectors can be, search of very, very rare particles. It can be used as a search of very rare particles. Right?
Yes. So
typically we look for not so rare particles as a dark matter with a tiny cross section, right? And here we look at larger cross section, but incredibly tiny amounts of these particles.
Yeah. So here, even you assume it's symmetric, will It will narrow.
It's not
easy
easy to organize that. It's probably, if I would be pressed against the wall to produce a model, I would say this has to be some kind of a low heat temperature model with maybe some exponentially small abundance of these particles.
Yeah, I'm not talking about the production. I'm talking about this indirect detection constraint. So because that's
the indirect detection constraint will scale as the square of this parameter.
Yeah, square of fx. Yes.
There is no hope. Yes.
No hope. But here you can form bound state, right? And then annihilate. Well, the bound state formation cross section.
For full disclosure, I should say that I have a postdoc here, Anupam Ray, and with him we're looking at what you roughly said, the annihilation of so the Earth. The idea is the Earth sort of collects the particles and then they annihilate. If the mass is a few GeV, you don't have to look for neutrinos from the annihilation. You can actually explore annihilation right inside the super K volume, and that turns out to be. So we are going to release that idea maybe within a month or two.
Okay. So looking forward to your paper.
You start probing me into the project that I'm doing right now.
Okay. Thank you.
Excuse me, I also have a question about this dark matter and nucleon bound state. So for this kind of bound state, will it be stable or unstable? If it's unstable, what is the decay pattern for that?
In that picture, it will be stable. However, kind of a KV kick to dark matter or to the nucleus rather can unbound it, right? But the binding energies would be on the KV kind of range. Yes.
I see. Thank you. So is there any further question?
In principle, that what people usually ask me, is there a sensitivity through rare isotope searches? And right, so like people know that among the water molecules or hydrogen in the water, right, from the bottom of the sea, there are no weird, GeV mass hydrogen whatsoever, right? With the sensitivity of 1 part per 10 to the, I forgot, 10 to the 25 or something like that. But here the thing is that these particles don't bind to light elements. Because the initial epsilon is 10⁻³ for us, so you compensate it by having a large Z of a nucleus, right? So we have investigated that if you move down in the table of elements, or move up rather towards lighter elements, you lose the bound states very quickly. So and for heavy elements, the exotic abundances are not checked as precisely as they are for hydrogen, and also these things will feature in this these bounds will feature here, but they will be featured into way excluded area by the xenon. Yeah,
I see. Thank you. Any further question or comment? Yeah, please.
Yeah, I want to ask a question. Hello, Maxim. Should I continue?
So let me see who is speaking. Yes.
Okay. So the question is, before their direct detection experiment, they usually go through a procedure, something like an isotope depletion or xenon purifying. So will this deplete the xenon and the dark matter bound state, which gets depleted through this procedure?
Good. Excellent. we are looking at the process of formation. We are not looking at the xenon. So we really, the picture is this: you have the dark matter detector, you have particles coming through, right? And from time to time, they have interaction that creates this burst of ionization. Now, this is relatively rare events, right? We are talking about, remember this counting rate, 10 events per kilogram, per ton per year, right? So you can average this over the, let's say, the lifetime of the Earth, which, so we multiply by, 10 to the 9, so you get 10 to the 9 particles per ton, right? Roughly, that's the abundance that you 10 to the 9 per ton is like 1 per gram or something like that, and that's not, this is no, 10 to the 3 per gram. So this is not. This is very, very hard to see in the isotopic separation business. I don't think they know that to that level. But in principle, you're right. So if you separate the harder fraction, your concentration of these things will go up. Yeah. Chemically, it's still, despite this bound state, it still is inert gas or inert liquid. Yes.
Okay, thank you.
So any further question?
Hello.
Hello.
Yes, please go ahead.
I have a question about why we so interested in the light dark matter. What problems it can help us to solve?
Oh, well, why indeed? So there were, over the years, there were a number of interesting ideas of what light dark matter can do. For example, if you have light milli charged dark matter, it can contribute to the late cooling of hydrogen and modify the 21 centimeter line. This is very speculative. So in 2018, the EDGES collaboration have seen the absorption line in cosmology of the two, they claim 21 centimeter, that is implying a baryon temperature lower than the standard cosmological temperature, which can only happen due to the coupling to light, effectively light dark matter. So dark matter in a few MeV mass with some effective electric charge of 10⁻⁴, 10⁻⁵. So that was one idea why this was attractive. Also, over the years, people have speculated that maybe some of the very strong emission feature of 511 keV line that we observe on the sky coming from the galactic bulge and not from the galactic disk, that might be the result of the light dark matter annihilation and so on. But so though these motivations are a little bit speculative, but my motivation is that since we invest so much into the dark matter searches, we may as well cover everything we can. Otherwise, you know, we don't have to do it twice. That's the idea.
Okay, thank you.
Okay,
Hi,
so it's
Maxim.
yes, please.
Yeah. Sorry, very naive questions and maybe a little bit crazy. So I'm thinking now constantly we use the particle or the wave picture as dark matter, to search the dark matter. Suppose we didn't find any evidence, no matter particle or wave dark matter in future experiments. Should we question these two pictures?
Well, there are always alternatives, right? I mean, there is a possibility that there are many other possibilities. I don't know, would you call primordial black holes as particles? It's neither particle, nor, you know, it's like it could be microscopic objects as well, right? There's certain fractions of black holes as entire dark matter. It's also not ruled out, right? Also, our searches, unfortunately, are all predicated on you know, interaction rate, right? They can be so there are viable models, unfortunately, that have so small interactions that it's very, very hard to see, right? So in that sense, conceptually, the whole field of the dark matter search is opportunistic, right? So people have discovered that you have the opportunity to look for this, and you pursue this opportunity motivated by this. But if you don't see it, you can say, all right, I killed this class of models, but it's very hard to kill the whole idea that this is a particle or a wave completely, right?
Okay.
So we would not have the total, if we don't see anything, we would not have the total closure of the topic. That's unfortunate.
Okay, I see. Okay, thank you.
Maybe someday one would show that, you know, there is no dark matter. But even the people who postulate this modified Newtonian dynamics and so on, I'm not a supporter of this, but even if you do that, this is in some sense a dark field, right? The dark fields that modify the interaction. So something dark going on there as well. So yeah.
Okay. Yeah. Okay, thank you.
Yeah, I have a naive question. So in this page of the final line, you mentioned a DNA. So the DNA is the biology DNA or other term?
Yeah. So that this was there some you know, people were throwing suggestions how you can do the various detections, and if dark matter has small mass and you don't give a keV energy to the nucleus, you can still damage atomic bonds, right? And so that there were papers on how you can sort of search for the using molecules, and even large molecules, you kind of accumulate the defects, right? It's actually, I mean, like, the idea of accumulating defects is very nice. There are all these constraints that people put in by using like perfect geological crystals, right? If there is a perfect crystal and it's been there for like millions of years, right? And you extract it, and if there were like collisions, then you would have some defects, displacements, and so on. And the DNA, I think it was along the same lines that you have some sort of some kind of a damage to a DNA. Yeah, it's very so people were really throwing like kitchen sink at this problem to trying to do all sorts of exotic things. You can see the papers. Yeah, we can use quantum dots to and these are good people who write these papers. You can use quantum dots to look for dark matter. The problem is that you need like the many kilograms of quantum dots with you know with very little background. That's the problem.
Yeah, thank you. That's interesting. So any questions or comment? So if no, let's thank our speaker again.
Excuse me, I have a question.
Okay, yes, please.
In page 25. Yeah, here, in the accelerators and dark matter detectors, what is the possible background when we detecting the dark matter?
That depends a little bit on what kind of how you use the beam as well. So if you study some reactions that don't produce neutrons in the final state, you don't the beam itself would not create that much background, we think. Okay.
Yes.
Or you would have a good absorber for the beam and then nothing much would come out of it. The problem would be the ambient radioactivity inside the cavern, right? I do not know, right? That's really is a question of where this can be done, but in Jinping lab, for example, is very deep. The main backgrounds would be from natural radioactivity, and so it would be like you would have to use some shielding, but how much shielding, as I said already, this would depend on the cross section, on optimizing signal versus background, basically. Yeah.
Yeah, thank you. But in fact, I have another naive question: is how can we make sure the dark matter is accelerated, and what is the possible signals?
Oh well, you see, you make an assumption here. You assume how much of this dark matter there is in the galaxy, and you assume the cross section and the mass. Well, these are the three things that you assume. And then you test your assumption. Yeah, that's a hypothesis, right? Then I say, okay, let me say these particles constitute 10 to minus 3 of the dark matter. The cross section as let's say 10 to minus 28 centimeters squared, and the mass is a couple of GeV. So there is a professor in New York, Glenys Farrar, that likes the models that have composite dark matter of 2 GeV mass, right? So it's precisely for her story. Now, with this type of parameters. Now, that's your assumption. You build that scheme, and you see nothing, right? And that you can then rule out this model, for example, or not, right? So you say that if my model is right, I predict that many events. You see the events below that level, you rule out that parameter space, right? If say Glenys Farrar is by any chance correct with her model, then you should start seeing events in that situation. Yeah.
Yes, thank you. And here, the dark matter is accelerated by the cosmic ray, right?
No, that is different picture. So here is here is the accelerator. Basically,
it is
hitting a dark
accelerated
matter
by
somewhere here. Let's say and well, here, right? And the dark matter propagates and enters the detector. In the cosmic ray picture, is you say, oh, I don't need accelerator, right? I have cosmic rays. Well, half of the low energy particles, including muons, pions, positrons, and kaons, and possibly even charm, were all discovered using cosmic rays, right? So you can say, oh, well, I have cosmic rays. And as a consequence of that, then you use the cosmic rays not on the Earth, right? Because you benefit from the whole volume of the galaxy, right? And then that creates a fast fraction of dark matter. This dark matter is not staying bound to the galaxy; it's flying away, right? But on the way out, some of them passes through us and leave the trace. That's the idea.
Here we use the nuclear to hit the dark matter and accelerate.
That's correct, yes. And
yes,
I
thank you.
argued that this is possible because of the large over-concentration of dark matter that one can have. So you see that the parameter here is 10 to the 14. So you can have 14 orders of magnitude enhancement just because the Earth existed for a long time. It accumulates the dark matter. Unless it annihilates, right? That comes back to Weipeng's question. Well, if it doesn't annihilate, it accumulates it for a long time, and then yeah, you can even initially small fraction will be amplified to a large degree. Yes.
Yeah. Okay. Thank you.
Any question? Last chance. Okay, so if no, let's thank our speaker again. Thank you for this very nice talk.
Thank you very much. Thank you for the opportunity. Thank you.
Thank you, Maxim. Thank you very
Thank you,
nice talk.
Maxim.
Thank you.
Okay. Bye, Maxim.
Bye, bye. It was great seeing you.
Bye.
Okay.
Great seeing you.
Bye. Oh, stop.
See you.
Okay.
Maxim, excuse me, so do you mind to share the slide with us?
I will send
This
you
talk
the
slide.
Yes.
Okay, thank you very much.
Thank you. Thank you.
Okay, so I will end this
Yes.
seminar. Thank you very much. Okay,
Thank
see you
you.
next time.
Absolutely.
Bye.
Thank you. Bye.
Bye.